In this video, we are going over Newton's second law, which is F equals ma. We're covering everything that you need to know to be prepared for MCAT style questions about this topic. If you like this content or are just needing more help preparing for the MCAT, you can subscribe to my MCAT community, and there's a link to do that in my bio or in the description to this video. Let's start by talking about motion in two directions, but this time we're going to apply force to it. We are saying that this ball is moving to the right and it's about to fall off of this surface. And the only force right now is gravity on this, because we are going to ignore anything like friction or air resistance. There's a normal force, but we're going to cover that later in this video, so for right now, just ignore it. All you want to know now is that the normal force and the gravitational force are the same amount, so they're going to be canceling each other out. Once the ball is off of the surface, so right here, that normal force is no longer there because there's no surface underneath of it, so now all we have is the force of gravity. And there is still no force in either x direction. Probably the most important equation that you need to be very familiar with is F equals ma, where F is the net force on an object, m is mass, and a is acceleration. What this makes it easy to see is since we have a force of gravity pushing down on this object, that makes this side of the equation positive, which means we will have an acceleration in the same direction as that force. The acceleration will always be in the same direction as that net force. Since we only have gravity, then gravity is going to be equal to our net force. Since gravity is only in the y direction, then this ball will only be accelerating in the y direction. Without any forces in the x direction, there is no change to the ball's velocity in the x direction. I mentioned this in the first video in this series, but let's revisit it. If there's an object that is moving 10,000 meters per second and it's in this direction, let's say after 20 seconds it's still moving 10,000 meters per second. The question is, what is the net force on this object? And the way that you have to be thinking about this is that since the velocity didn't change, it's at 10,000 at both points, then the acceleration was 0. If we plug 0 into our equation up there, then that means that force is also 0. So even if you're moving at 10,000 meters per second, if you have no acceleration, then there is no net force on that object. So let's say that you're in deep space and there's nothing around you, and you push a ball and it's moving at 50 miles per hour. It's going to continue to move at 50 miles per hour forever unless there's a force that can oppose that motion. And it doesn't require any additional force to keep that ball moving at 50 miles per hour, as long as no other force opposes it. Now let's look at breaking down a vector into multiple components when it comes to force. And we're told that we're pulling it with a 10 Newton force as represented by that vector. That force is at a 30-degree angle with the ground. We're going to ignore friction with this problem, and here's just drawing the ground. It's always helpful to just think about what forces are involved, and we have the gravitational force and our pulling force. Now we also have a normal force and you will have a friction force, but we're not talking about friction in this video. That's going to be the next video. We are only focused on the sled's motion in the x direction. That leaves us with only the pulling force to focus on. We need to break this force down into its components, so I'm drawing a dotted line for the two sides of this vector. This turns it into a right triangle that has an angle of 30 degrees right there. Since we are only wondering about the sled's motion in the x direction, then we only have to worry about this side of the triangle. Since the sled is not moving up or down in any way, we can completely ignore the vertical component of that vector. The x component of that triangle is adjacent to that angle, so we're going to use cosine. Write out the mnemonic 1975 and then add 0. That is cosine of 0, 30, 45, 60, and 90. And then just throw a decimal point in front of those. So we have cosine of 30 is equal to adjacent over hypotenuse, which will be x over 10 newtons. That's 0.9 times 10 newtons equals x, giving us 9 newtons for x. So our sled is being pulled with a force of 9 newtons in the x direction. We then do 9 is equal to the mass times acceleration, so 5 times a. A is equal to 9 over 5, and with some rounding, that's going to be roughly 2 meters per second squared. If you wanted to find the y component up here, you would just replace this part of the equation with sine and solve it just like we did. The last thing we're going to talk about in this video is the normal force. The normal force pops up anytime you have an object that's in contact with a surface, assuming that object is exerting some force on that surface. The normal force will push back on that object, and notice how it's forming a right angle with the surface. So the normal force is always perpendicular to the surface. Let's look at the stick figure here to talk about the value of that normal force. This stick figure has a mass of 70 kilograms, and we multiply that by 10 meters per second squared to figure out that the stick figure has a weight of 700 newtons. So the force of gravity is pulling down on that stick figure with a force of 700 newtons. That means that the stick figure is applying a force to the surface of 700 newtons. So this arrow that represents the force that the stick figure is applying on the surface is completely perpendicular to the surface, which means the entire 700 newtons is being applied to that surface. So then the normal force that opposes that is also going to be equal to 700 newtons, like we see there. If you had a different situation, let's say that somebody was pushing down at an angle like this. If they're pushing with a force of 10 newtons, the entire 10 newtons is not perpendicular to the surface, only the y component of that force, because the 10 newtons is only the hypotenuse of this right triangle. That means you're going to have to use your trig functions to figure out what is the y component of this triangle. Let's say that this angle here is 60 degrees. You would then do sine of 60 is equal to y divided by 10. So you have 10 sine 60 is equal to y. Sine of 60 is about 0.9, so we would do 10 times 0.9 equals 9. So the y component of that triangle is 9 newtons. Even though we have a 10 newton vector pushing on the ground, only 9 newtons of that is pushing straight down, forming a 90-degree angle with the ground. That means that the normal force opposing this pushing motion is only equal to 9. You also want to be able to solve this whenever we're not dealing with a horizontal surface. Over here, we have a person pushing a book against a vertical wall. The person is pushing the book at an angle. That means that once again, we're going to have to use some trig. Let's say that the angle here is 30 degrees. Let's use 10 newtons again for the force that the person is applying to the book. We are looking for the x component of this triangle because that is the component of the pushing force that is perpendicular to our vertical surface. We use cosine to find that adjacent side, so we do cosine of 30 is equal to x over 10 newtons. Cosine of 30 is about 0.9, so once again we do 10 times 0.9 is equal to x. X is equal to 9 newtons. That means that the normal force pushing against that book is equal to 9 newtons because that is equal to the component of that pushing force that is perpendicular to the surface.